We've seen all sorts of explosions so far, from megaton to kiloton nuclear bombs, dropped in the atmosphere, exploding far above ground or closer to it, detonated on towers or on barges, even shot from cannons. We've seen underwater explosions and shown that the blast propagates slower if the ambient medium is denser, like water compared to air. We've seen the same destructive dynamics unfold for conventional explosions, based on chemical rather than atomic energy, like the terrible 2020 explosion in Beirut. For nuclear explosions, a bomb with a mass of a few tons can produce energies equivalent to millions of tons of TNT. But with conventional explosives, what you see is what you get. The smaller the mass, the smaller the explosion. Here, you see an explosion from a mass around 1 gram, now 10 milligram. Even smaller explosions can be produced by laser pulses, such as this one, with an energy around 0.5 millijoule, which is equivalent to 0.1 microgram of TNT. For all these explosions, large, small, smaller, away from the ground or not, we've seen that the size of the explosion reflects a dynamic ratio between two opposing factors. The input of energy, E, is the motor of the explosion, the impelling factor. The density of the ambient medium, ρ, pushes back against the explosion. It is the impeding or impairing factor. Energy versus density. As shown by Taylor, the kinematics of an explosion can be understood as stemming from the mechanical ratio of energy and density. The dimensions of energy and density combine in such a way that the blast radius d is equal to E divided by ρ to the power 1 over 5 times t to the power 2 over 5. By gathering the evolution of the blast radius over time, we can check that indeed d is proportional to t to the power 2 over 5, with a kinematic prefactor k with a different value for each explosion. We saw this first with Taylor and Trinity, the first atomic test of 1945. By plotting the blast radius measured on successive pictures, we saw that indeed the radius d was proportional to t to the power 2 over 5. The radius of the explosion follows a power law. Fitting the data with a straight line in log scale, we could obtain the value of k for the Trinity test. It was around 583 meters per second to the power 2 over 5. It was from this measurement that Taylor could estimate the yield of the Trinity explosion. In episode 2, we considerably enlarged our scope to include a large spectrum of explosions, from tiny to huge, nuclear explosions, underwater explosions, conventional explosions like those produced by TNT, and even microscopic laser-induced explosions. In each case, we could measure the value of the prefactor k, best fitting the data. The value of k for each explosion is here color-coded, from faint to darker reds. We then asked if, for each explosion, the value of k could be understood as the ratio between the energy of the explosion and the density of the surrounding medium, as suggested by Taylor. The energy E ranged from less than a millijoule to 10 to the power 17 joules for the biggest nuclear bombs. The density, depicted here, ranged over almost 6 orders of magnitude. Most examples of explosion we talked about in the previous episode happened in the air, where the density is around 1 kilogram per meter cube, here color-coded in red. We also talked about a couple of underwater explosions where the density is around 1 ton per meter cube, in green. And one of the laser-induced explosions was conducted in rarefied xenon, where the density is just a few grams per cubic meter. We ended the last episode with this plot, which gathers the value of the prefactor k fitted on the blast radius data of each explosion. Each value of k is then compared with the ratio of energy and density associated with each explosion. If Taylor's regime applies, all data points should fall on a line of logarithmic slope 1 over 5, since the prefactor k is supposed to be E divided by ρ to the power 1 over 5. Most data points do follow this scaling, although not perfectly. Some explosions seem to deviate from Taylor scaling. But by how much? For each explosion, we can define a number delta to quantify the agreement with Taylor's regime. If delta equals 1, the agreement is perfect. And as delta becomes smaller or larger than 1, the deviation with Taylor's predictions become more worrisome. In this third episode on explosions, we will talk about this number delta. Delta is an example of dimensionless number, which we will call the Taylor-Sedov number. We will show that this number can be viewed as a variable and as a constant, quantifying the agreement between the kinematics of the explosions and the mechanical scaling put forth by Taylor in the west and simultaneously by Sedov in the east. Let's start again with Trinity. So far, the data we've been analyzing are those of the blast radius d versus time since detonation. This perspective is particularly visual. Take any data point and you can literally see the radius on each picture and face it with the time at which the picture was taken. From this perspective, the observed power law is 2/5, meaning that the radius is proportional to time to the power 2/5. But other perspectives are equally valid. Instead of representing the radius d of the hemispherical approximation, we could record the speed of the leading edge as it moves away from the location of the bomb. A few different speeds can be defined. The speed of the edge can be estimated from the difference in radius and time between consecutive pictures. Between these two pictures, the edge moves at speed around 8,500 km per hour. This is more than 2,000 meters in 1 second. Quite fast indeed. If you compute the speed in this way for all pictures used by Taylor, you would get a plot like this. The 2,000 meters per second we used as an example is down here. On this plot, the speed is registered at a time corresponding to the latest of the two images used in the difference. In our example, this was 25 milliseconds. But if the speed is measured between 15 milliseconds and 25 milliseconds, when is this speed happening? Instead of using 25 milliseconds for the horizontal coordinate, you could also use the earliest of the two times, thus shifting all the curve to the left. Or the mean time between the two pictures. In linear scale, this is just the arithmetic mean. In logarithmic scale, this is the geometric mean. Comparing the value of these different schemes to define a speed is beyond our point here. Regardless of the scheme, the speed is decreasing as a power law, with a negative exponent. We put accents or primes on k and alpha so as to not confuse them with k and alpha defined for the radius plot, d versus t. But the prefactor and exponent for the speed are connected to the prefactor and exponent for the radius, because the speed v and size d are connected, as we will see now. Let's come back to d versus t. When the data abide to a power law, d is equal to k times t to the power alpha, we can compute the derivative of d of t, which gives a speed v equals to k times alpha times t to the power alpha minus 1. So k times alpha is what we called k prime, and alpha minus 1 is alpha prime. So looking back at the speed versus time, we can understand the negative slope of the line as being 2/5 minus 1, that is minus 3/5. And the new prefactor is just k times 2/5. Looking back at the formula for the speed, we see that it can be expressed as alpha times d divided by t, since d is just k times t to the power alpha. The h speed is not just d over t, because the radius does not expand at a uniform rate. The factor alpha takes this into account. Then, for each data point associated with the value of d and t, we can compute a speed. Calculating the difference between consecutive frames produces a speed, but the process generates considerable noise. Defining another speed as alpha times d over t produces a smoother plot, respecting the -3/5 scaling. If the radius data follow the 2/5 power law, defining a speed as 2/5 times d/t and looking how this speed evolves over time provides a different perspective on the explosion, equivalent to directly representing the evolution of the radius. This freedom in the choice of representation can be pushed even further. We can represent space versus time, that is d versus t, or the ratio of space over time, that is v versus t. Actually, we can choose any combination of space and time to be represented. One combination is particularly useful. It has no standard name, but we call it the explosivity. In the first episode on explosions, we said that the prefactor k in the power law is an example of kinematic quantity, that is, a quantity with dimensions depending solely on the dimensions of space, L, and time, t. Speed is also a kinematic quantity with dimension L/t, or L t-1. Acceleration is another one, with dimension L t-2. There are other examples like diffusivity, which is an area over time, so with dimension L square t-1. For explosions abiding to Taylor's regime, the dimensions of k are L t-2/5. Because the dimensions contain non-integer exponents, we say that this kinematic quantity is non-standard. When the exponent is a fraction, a simple procedure consists in considering a large enough integral power of k such that its dimensions are integers. This can be done by considering the fifth power of k, which becomes a standard kinematic quantity, since 5 and -2 are integers. A quantity with such dimensions is what we called an explosivity. All this may seem a little bit silly, but these conventions become particularly useful when considering not just one power law, but many and the relationships that they have with one another, something we'll do in the long run. Now we've seen how the kinematics of the explosion can be represented as a size over time, or as a speed over time. We can also represent the explosivity over time. Here, the explosivity is defined for each data point as the ratio between the fifth power of the radius d and the square of the time t. So units are meter to the power 5 divided by second square. In this representation, Taylor predicts a constant explosivity equals to k to the power 5, where k is the prefactor of the power law of d versus t. According to Taylor, this prefactor is connected to the ratio of energy and density. Taking the fifth power and rearranging the equation, we see that the constant explosivity k to the power 5 should be equal to the mechanical ratio E divided by rho. The dimensions of the constant E and rho are such that the ratio is a constant explosivity. If we use a linear scale for the explosivity axis, it becomes quite clear that the instantaneous explosivity is only approximately constant. It slightly deviates from the ratio of energy and density put forth by Taylor. For each data point, we can introduce a number n, quantifying the degree of agreement with Taylor's regime. We call this number the Taylor-Sedov number. So far, we've been calling this relationship between space, time, and the ratio of energy and density Taylor's regime, or Taylor scaling, depending on our mood. Taylor publicized this equation in a couple of papers published in 1950. The abstract of the first paper made it clear that the 2/5 scaling was put forth during the war in 1941, and we know that it was available at the time of the Trinity test. The World War really boosted the interest for big explosions, and so seeking an understanding of their kinematics was in the air. Pretty much at the same time that Taylor in the UK, the Hungarian-American physicist John von Neumann was also working on the problem and got the same 2/5 scaling. In the East, the Soviet physicist Leonid Sedov also got the same result. So we've called the 2/5 scaling Taylor's regime, but we could have called it the Taylor-Sedov von Neumann regime, but this compound noun is a bit cumbersome, so we'll stick to Taylor's regime, and we will eventually just call it the energy density regime, or E-rho regime, so as not to make anyone jealous. Now, we've seen that when Taylor's regime is written as an explosivity over time, the dynamics show a roughly constant explosivity close to the mechanical ratio of energy and density. The quality of the agreement is given by the number n. In fact, for any blast radius dataset associated with an input energy E and ambient density ρ, we can use the variable explosivity built from the kinematic ratio of d to the power 5 divided by t squared and divided by the constant mechanical explosivity to define a value of n for each point. By construction, this number has no dimension. We said that it is dimensionless. It would be tempting to call this number the Taylor number, but this name is already taken. It means something else. So to avoid cumbersome names, we shamelessly forget about von Neumann and call this number the Taylor-Sedov number. It is an example of simple dimensionless number based on just two mechanical quantities. Now, instead of plotting the instantaneous explosivity over time, we can very well plot the value of the Taylor-Sedov number, n versus time. Switching to a linear scale for n, we see that most data points are close to the line n equals 1, which is just another way of saying that most data points follow Taylor's regime. Now, looking beyond Trinity, the last episode collected a bunch of datasets of explosions, which are represented here in a plot of the radius d versus the time t. For each explosion, we have constant value of input energy and ambient density. So for each explosion, we can compute the value of the Taylor-Sedov number and represents its evolution over the course of the explosion. Let's look first at atmospheric nuclear explosions. Housatonic, Maple, Climax, Trinity, Grable, Apple were the 6 tests we discussed in the last episode. From this perspective, plotting d versus t, all these tests seems to abide pretty well with the 2/5 power law. Now, plotting the evolution of the Taylor-Sedov number for all these tests allows a more in-depth comparison with the predictions of Taylor's regime. We've seen Trinity already. The agreement is pretty good. This is Apple from Operation Teapot. Here the plateau seems to be a value of n slightly larger than 1. This is also the case for Grable, Climax, and Maple. For Housatonic, the plateau is lower than 1. Here are all 6 tests. Let's use continuous lines to see a bit more clearly. Note that the Taylor-Sedov number is represented in linear scale, so the plateaus for each explosion are actually all fairly close to 1. We will actually use this proximity to 1 as a criterion to determine if an explosion follows Taylor's regime. If the instantaneous Taylor-Sedov number shows a plateau with a value close to 1, then the dynamics are indeed due to the balance between the energy input E and the ambient density ρ. The value of the plateau of n, which we can call n naught, is what we call the Taylor-Sedov constant of an explosion. Let's go back to our favorite example, Trinity. What is the value of the plateau for the dimensionless number n? We can plot a distribution of the value of n throughout the duration of the explosion. The first 2 points are clearly off. We'll come back to them soon. If we leave them out, we can obtain the mean value of n and its standard deviation to compute the value of the Taylor-Sedov constant with an associated range of uncertainty. Trinity is in pretty good agreement with Taylor's regime. Take Housatonic now. Using the same procedure, we can compute the Taylor-Sedov constant to be around 0.23. We can do this for all explosions we introduced in the last episode to get a plot of the value of the Taylor-Sedov constant for each explosion, here shown as a function of the energy E of the explosion. Most values are close to 1, and remember that the Taylor-Sedov constant is a spatial value of the Taylor-Sedov number. If we rearrange the terms, we see that the Taylor-Sedov constant is just a dimensionless correction to Taylor's regime, and note to the power 1/5 is the number that we called delta in the last episode. It gives the agreement between the observed prefactor k and the mechanical ratio of energy and density. Delta is what we could call a reduced Taylor-Sedov constant. If we plot it, we see that all explosions are not far from Taylor's regime. Historically, the value of delta has been connected to the thermodynamics of the ambient medium around the explosion. But it's actually a black box that can contain all sorts of subtle effects. To understand why sometimes explosions do not quite follow Taylor's regime, we first have to investigate situations where Taylor's regime is clearly violated. Take Trinity again. Clearly, the very short timescales do not have a constant Taylor-Sedov number, which is to say that they do not follow Taylor's regime. We will discuss this in episode 5. What happens at the other end is what we will see in the next episode.